In order for fatty acid oxidation to occur, the fatty acids have to come from somewhere. Most fatty acids are stored within adipocytes or fat cells as triglycerides, or a glycerol molecule with 3 fatty acids attached to it. In order to get one of those fatty acids free from the triglyceride, you've got to use something called a lipase, or an enzyme that cuts a lipid. The most common fatty acid that's within a triglyceride is palmitate, or a 16-carbon fatty acid. In order for palmitate to make it to the target cell, it's got to hitch a ride on albumin and travel through the blood. Blood's mostly made of water, and fatty acids are mostly hydrophobic or afraid of water, so they need some kind of carrier molecule to get them to the target cell. Once it reaches the target cell, palmitate is able to easily diffuse across the cell membrane and into the cell because, again, it's hydrophobic. The cell has to have some kind of mitochondria because this is where the fatty acid oxidation is going to occur. Inside the intermembrane space of the mitochondria, there are CoA molecules, and as the palmitate enters the mitochondria, it combines with a CoA molecule to make palmitoyl-CoA. This reaction actually occurs over a couple steps and uses ATP getting converted to AMP, which in bioterms means you're using the equivalent of 2 ATPs. Palmitoyl-CoA can't enter the mitochondrial matrix on its own, so it has to use something called the Carnitine Shuttle in order for it to enter the mitochondrial matrix. First step in the shuttle, the palmitoyl-CoA gets converted to palmitoyl-carnitine using the first carnitine-palmitoyl transferase, or CPT1. Palmitoyl-carnitine is able to enter the mitochondrial matrix, where it is converted back into palmitoyl-CoA. The enzyme that was used to bring palmitoyl-carnitine into the mitochondrial matrix is also going to be used to move carnitine back out into the intramembrane space, and it's called carnitine acylcarnitine translocase, or CACT. The enzyme that's used to transfer the CoA molecule back onto palmitate is called CPT2. And now that palmitoyl-CoA is in the matrix, beta oxidation can occur. In the first step of beta oxidation, palmitoyl-CoA is going to react with FADH plus to make FADH2. The first carbon in this chain is double bonded to the oxygen, so although it's carbon number 1, alpha carbon is carbon number 2, making the beta carbon carbon number 3. This is beta oxidation, so we're going to be losing electrons from that beta carbon, which is going to make a carbon-carbon double bond, which means another hydrogen or H plus molecule also has to be lost. In the next step, we're going to use water to break that carbon-carbon double bond, adding an OH group to that beta carbon and the hydrogen back to that alpha carbon. In the next step, once again, we're going to lose a hydrogen molecule, but this time the hydrogen's coming from that OH group. It's going to take the electrons with it, which is going to make NADH from NAD+, aka oxidation. In the final step, we're going to use a CoA molecule to cut between that alpha and beta carbon, making an acetyl-CoA molecule and a fatty acyl-CoA, or in this case, a 14-carbon fatty acid with a CoA attached. Because sulfur is used to make this cut happen, this is called thiolysis. Now that we've made that acetyl-CoA molecule, it's going to hop on over to the citric acid cycle, where it's going to be combined with oxaloacetate to make citrate and go through the cycle all over again. The 14-carbon fatty acyl-CoA is going to keep going through the beta oxidation step 5 more times until it makes 2 acetyl-CoA molecules. Scientists have theorized how much ATP you can make from fatty acid oxidation using a specific kind of math. This math only applies if the fatty acid chain has between 12 and 22 carbons in it. Before you even start oxidation, you've got to use 2 ATP equivalents for the initiation. At the end of beta oxidation, you're going to have 1 FADH2, which by biomath means you're going to make 1.5 ATP. You're going to have 1 NADH by biomath that makes 2.5 ATP for a total of about 4 ATP per round of beta oxidation. Each round is also going to make 1 acetyl-CoA molecule, which goes into the citric acid cycle. And from the citric acid cycle, you're going to make another 1 FADH2 for another 1.5 ATP. You're going to make 3 NADHs for 7.5 ATP, and you're going to make 1 GTP, which is equivalent to 1 ATP. So after the citric acid cycle, you're going to make another 10 ATP equivalents. Combining the 10 and 4, each round of beta oxidation is going to make 14 ATP equivalents. Now let's say you want to calculate how much ATP you make in total. You start with the number of carbons that you have in the chain, and you're going to divide that by 2. You're dividing it by 2 because each time you do beta oxidation, you're cutting up 2 carbons at a time. You're going to subtract 1 because the last round of beta oxidation is going to make 2 acetyl-CoA, so it's not going to go and make another 14. It's going to go straight to the citric acid cycle. You're going to add 10 because that last round is going to add 10 instead of 14, again, from the citric acid cycle. And you needed to have 2 ATP for initiation, so that's going to remove 2 or minus 2. If you simplify this equation, you're going to end up with 7N minus 6. So you can use this equation every single time to figure out the ATP yield if the carbon chain has between 12 and 22. If there's less than 12, then you don't need initiation, so it's just 7N minus 4. And if it's more than 12, you have to use peroxisomal oxidation, which is a different math completely.